time to continue. So Gábor is already ready. Gábor Steinbach, who is an expert in the differential polarization analysis and microscopy, in which he took a very essential part of building this type of things. So Gábor, the floor is yours.
Referring to Gábor's talk, it's based on confocal lasers and microscope, and using the advantages of the laser excitation and using the method of the imaging process in a confocal microscope, build the image pixel by scanning. I don't want to speak about the theory of the LSMs we heard this morning, but I would like to emphasize this point-by-point data collection by the scanning mirror and the synchronized data acquisition. It will be important for the DPLSM as well. Why to build DPLSMs? It's very important and useful to gather more information of a sample than just absorption. The interaction with the polarized light contains more structural information in the background. We would like to gather those information as well. An example of how to interact dipole in your sample with the polarized light. For example, a dipole-shaped fluorophore can be excited by linearly polarized light with the same direction, the sheet of the linearly polarized light. If it's parallel to the dipole, then it will be in the excited state, and we can have the fluorescent light at the end. In another case, if the dipole and the polarization plane is perpendicular, it won't be excited, it won't have fluorescent light in the microscope. Measuring the fluorescence answer of our molecule, we can have the behavior of the sample, what kind of interaction it will make with the different kinds of polarized light, polarized excitation. Changing the convention, the measurement structure of the equipment, we can use linearly or circularly polarized light for the sample. We can modulate that light, or we can analyze the fluorescent light on the other side. These possibilities provide several different polarization parameters, which are listed here. And most of them can be measured in confocal regime using all the advantages of the confocal microscope in lateral and Z resolution. It's not really for scaling view, this set of equations. The most important take-home message of this slide is to see all the differential polarization parameters are based on the difference of measured intensities, for example, the intensity of fluorescent light connected to the orthogonal polarization statuses, and those are normalized to the average intensity. All the kinds are something like this. For some yesterday, some of you saw it in the real life. I would like to go step by step through what was those parts, what they met yesterday. The scheme of the system is the union of two different set of elements. The color coding will show it. The DPLSM unites basically a microscope. It's blue and the diagram with red and green colors. If you don't see the red and green stuffs, it's basically a simple confocal microscope, laser excitation, lightweight beam splitter to the center, and backwards we have the photon multiplier tube as a detector. But it's possible to modulate and generate different polarization statuses for the excitation laser going to the center and or analyze the polarization statuses of the fluorescent emission on the detector side, and all the signals gathered by the PMT or by the transmission detector are analyzed by the phase-sensitive amplifier, which is synchronized to the modulation. For the different measuring modes, we have to put in or get out some parts. It can be find the differences again for the next some slides, what was removed and put on for the LDLD measurements, for the mapping of the direction of the absorption dipoles. You have to modulate the excitation light and don't do anything on the emission part. For transmission measurements, the same modulation was needed, but the transmission detector's signal is analyzed, not the fluorescent one. You can use non-modulated polarized excitation and the analyzation of the fluorescence to determine the degree of polarization, or depolarize the excitation, and like this, all the fluorophores were excited on the same way, and you can read the polarization status of the emission to determine the orientation is some phase shift between the components, then the horizontally polarized light will become elliptically going forward. If we have exactly lambda quarter, you can see those distances are really same. Then we will have the circularly polarized version of the original light, and we can go forward to have linearly polarized light again, but it's perpendicular to the original light. As you saw, it was not a rotation, it was modified through elliptical and circularly polarized statuses from one linearly polarized status to the other one. The coordinate system was with 45 degrees to the original polarization plate, so all the time we have to consider this 45 degrees to put the modulator in a diagonal position to the original coordinate system, what we would like to use for imaging, what kind of rays we would like to use for vertical and horizontal components of the dipoles during the imaging. If you have the same light through box with nothing, then no change will happen. It's easy. All the components can pass this box of air without any phase shift, without any change. If we fill the space with some material having refractive index more than 1, then the wavelengths will decrease a little, but that decrease will happen for all the components, for the vertical and horizontal as well. So the polarization status won't change at all. Of course, there is a phase shift between the previous state, but nobody cares. We won't use the phase of the light. We would like to change the polarization plate itself. To generate something else than this linearly polarized light, we have to put some shift between the components. For example, with some birefringent crystal. Of course, it's not really to have one as an ordinary refractive index, but consider for the image for a while. In this case, the images if it's well calculated what we will have. And I would like to show some photos about the other DPLSM laboratory in Budapest at the immunology department. It was made on a Olympus FT500 microscope, and you can see in different channels it's possible to image the different information of the measurement, longitudinal fluorescence measurement, the DP channel from the locking amplifier. The microscope won't know it's an external channel. So it's some special detector and nothing else, and transmission and imaging cells with different treatments, different conditions. You can do quantitative measurements between some cross-linkers in the membrane, for example, to measure the effect of them. In the recent times, several publications were launched in this topic, and we worked together with quite a lot of people. Those were for the technical side. We collaborated from companies and the different departments. We are very thankful to them to lend their microscope to us and have the possibility to build DPLSM on them. And the different samples were from very different labs all around the world. We are really grateful for them for the collaboration with us. And thanks for the writer of the latest program I made for the 3D schemes. Thanks for your attention.
Yesterday you had the chance to see these labs, so I guess that many of you had questions. I have put it already, but nevertheless, if you have any further questions, yes, please.
What is the limiting factor for the speed of analysis that you mentioned takes 1 minute for the analysis?
The frequency of the modulation is stable,
Okay.
and you have to wait for some cycles of the modulator to reach pixel. And that makes slower the scanning of the focal measurement.
Do you expect that with the improved electronics it can be faster, or is that fixed limiting factor that you cannot reach?
It's based on the electronics and the optomechanics of the modulator. With a faster modulator, of course,
Very
it's
fast.
faster.
Okay.
What we did for a faster measurement with a modern locking amplifier, we could gain some factors in the calculation time if the locking amplifier provided a lower signal-to-noise ratio, and we shouldn't wait for so many cycles. That was
So roughly about 30 microseconds is presently the limit, the technical limit, because of the stability of the for example, the ballistic modulator at high frequency is not so stable, unfortunately. But 30 microsecond per pixel is already something which is not that sensitive. So it provides you a relatively fast measurement. Yeah. So if there are no further questions, we proceed, and I invite Peter Horvath to